You drop a cup. It shatters on the floor, pieces scattering across the tile. And then you wait. You wait for the pieces to jump back together, fly up into your hand, and become a cup again. You're going to be waiting a long time. The number of years you'd have to wait has more digits than there are atoms in the observable universe. So, it's not going to happen. But here's the thing. Here's the part that should bother you. Nothing in physics forbids it. Not one law. Not gravity. Not electromagnetism. Not quantum mechanics. Not the nuclear forces. Run the equations backwards and they work perfectly. Every fundamental law of physics is time symmetric. A cup can shatter. A cup can also unshatter. The math doesn't care which direction you play the film. Yet you have never, not once in your entire life, seen a shattered cup spontaneously reassemble itself. Why not? This isn't some minor puzzle. This is one of the deepest unsolved problems in physics. Arthur Eddington, the British astrophysicist who helped prove Einstein's theory of general relativity, gave this mystery a name in 1927. He called it the arrow of time. And he said something remarkable about it. He said the distinction between past and future holds the supreme position among the laws of nature. Supreme position. Not gravity, not quantum mechanics, the arrow of time. The fact that eggs scramble but don't unscramble, that smoke disperses but doesn't gather, that we remember yesterday but not tomorrow. Eddington called it an unsolved problem. Almost a century later it remains unsolved. You might think, well, obviously time moves forward. Obviously the past is different from the future. You remember eating breakfast this morning, you don't remember eating breakfast tomorrow. That's just how time works. But that's not an explanation, that's a restatement of the mystery. The question isn't whether time has a direction. Clearly it does. The question is why. Why does the universe permit reversibility in its laws but produce irreversibility in its behavior? Why is there an arrow at all? And here's what makes this truly strange. If you look at the actual laws, the equations that govern how particles move and fields interact, they are reversible. Newton's laws of motion, perfectly reversible. Maxwell's equations for electromagnetism, perfectly reversible. Einstein's general relativity, reversible. The Schrödinger equation in quantum mechanics, reversible. Even the strong and weak nuclear forces, with one tiny exception we'll get to, are reversible. You can take any process described by these equations, reverse time, and the equations still work. A photon can be emitted by an atom or absorbed by an atom. The math treats both as equally valid. A planet can orbit a star clockwise or counterclockwise. Physics doesn't prefer one direction over the other. So if all the fundamental laws are reversible, why is the world so obviously not? Why do we see cups shatter but never reassemble? Why do ice cubes melt in warm water, but warm water never spontaneously forms ice cubes? Why does smoke from a candle spread out into the room but never gather back into a thin column? Something is happening at the macroscopic level that the microscopic laws don't demand, and the answer, the reason time has a direction, comes from statistics, not from physics, from statistics. This was the insight of Ludwig Boltzmann, an Austrian physicist working in the 1870s. Boltzmann was trying to understand thermodynamics, the study of heat and energy, from the perspective of atoms and molecules, and he realized something profound. Entropy, the measure of disorder in a system, isn't really about disorder in some vague sense, it's about probability. It's about counting. Specifically, it's about counting how many different microscopic arrangements of particles can produce the same macroscopic appearance. Think about a deck of cards. There's one arrangement that's sorted by suit and rank. Clubs from ace to king, then diamonds, then hearts, then spades. One specific arrangement. But there are trillions upon trillions of arrangements that are shuffled, mixed, disordered. If you shuffle a deck of cards, the odds of it landing in perfect sorted order are about 1 in 10 to the power of 68. That's a 1 followed by 68 zeros. You could shuffle a deck once per second for the entire age of the universe and never see it sorted. Not because sorting is forbidden, there's no law against it, but because there's only one sorted arrangement and billions upon billions of shuffled ones. Probability overwhelms everything. Boltzmann saw that the same logic applies to molecules in a gas, atoms in a solid, energy distributed in a system. There are vastly, astronomically more disordered arrangements than ordered ones. Entropy measures this. It measures how many microstates, how many specific arrangements of all the individual particles correspond to a given macrostate, a given large-scale appearance. Boltzmann wrote it as a formula. S equals K log W. S is entropy. W is the number of microstates. K is Boltzmann's constant, a tiny number that sets the scale. The formula is engraved on his tombstone in Vienna. It's that important. When you drop a cup and it shatters, the pieces scatter into one of countless possible configurations. When you imagine those pieces flying back together, you're imagining one extraordinarily specific configuration out of all possible arrangements. It's not impossible, it's just breathtakingly, incomprehensibly unlikely. The shattered cup has high entropy because there are so many ways for the pieces to be scattered. The intact cup has lower entropy because there are far fewer arrangements where all the atoms are bonded together in just the right shape. The universe doesn't prefer disorder because disorder is somehow better. The universe keeps finding itself in disordered states because there are so many more of them to find. This is the second law of thermodynamics. Rudolf Clausius, a German physicist, stated it in 1850. In an isolated system, entropy never decreases. It either stays the same or increases, always, no exceptions. Eddington called this law the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe disagrees with the second law of thermodynamics, he said, "I can give you no hope. There is nothing for it but to collapse in deepest humiliation." He wasn't exaggerating. Every observation, every experiment, every process we've ever seen obeys the second law. Entropy increases. The arrow points forward. But now we arrive at the deeper question. If entropy always increases, if systems always move toward more probable, more disordered states, then why isn't the universe already at maximum entropy? Why isn't everything just a uniform gray soup of particles at the same temperature, no structure, no stars, no planets, no life, no cups to drop? If entropy has been increasing for the entire history of the universe, we should be at equilibrium by now. Maximum disorder, heat death. The state where nothing can happen anymore because there's no energy gradient to make anything happen. Yet here we are. The universe is full of structure, full of low entropy configurations, stars burning, galaxies swirling, life metabolizing. Why? The answer is that the universe started in an extraordinarily low entropy state. It began with far, far less entropy than it has now. And everything that has happened since, every star that has ignited, every planet that has formed, every thought you've ever had, is that initial order unwinding like a spring slowly releasing tension. This is called the past hypothesis. The term comes from philosopher David Albert in the year 2000, though the idea is older. It says the reason entropy increases toward the future is because entropy was lower in the past. Specifically, entropy was astonishingly, inexplicably low at the Big Bang. And this is where it gets truly mysterious. We don't know why. We don't know why the universe began in such a low entropy state. Roger Penrose, the British mathematical physicist, has argued that this low entropy was gravitational. See, when you're thinking about gravity, the intuitive notion of order gets flipped. A gas uniformly distributed through space seems disordered, and it is if you're not considering gravity. But if you are considering gravity, uniform distribution is actually low entropy. Why? Because gravity wants matter to clump. It wants to form stars, black holes, dense structures. A uniform gas has enormous potential to clump, and that potential represents order, low entropy. As the universe evolves, matter clumps together under gravity. Stars form, black holes form, and the entropy increases. Penrose calls this the Weyl curvature hypothesis. At the Big Bang, space-time was incredibly smooth, incredibly uniform in its curvature. That smoothness was low entropy. As the universe expands and evolves, space-time gets wrinkled, clumpy, full of gravitational wells and black holes. That's high entropy. The current entropy of the observable universe is approximately 10 to the power of 104 times Boltzmann's constant. That's a 10 followed by 104 zeros. Almost all of that entropy is in supermassive black holes. Black holes are the highest entropy objects in the universe because they can be formed by an enormous number of different configurations of matter. Once matter crosses the event horizon, the details don't matter anymore. All that matters is the black hole's mass, charge, and spin. The information is scrambled. Entropy is maximized. But even 10 to the power of 104 is nothing compared to what the entropy could be. Penrose calculated that if the universe were at maximum entropy, the entropy would be around 10 to the power of 123. We are nowhere close. The universe still has an incomprehensibly long way to fall toward equilibrium. The spring is still unwinding. The arrow is still pointing. You might be thinking, okay, but what about life? Doesn't life violate entropy? Living things are organized, structured, ordered. A baby starts as a single cell and grows into trillions of cells arranged in specific patterns. Doesn't that decrease entropy? No, it doesn't. Life is a local entropy decrease paid for by a larger entropy increase elsewhere. Think about a plant. It absorbs sunlight, low entropy energy. Photons from the sun are concentrated, directional, carrying energy in an organized way. The plant uses that energy to build sugars, to construct leaves and roots to grow. That's a local decrease in entropy. The plant is more ordered than the carbon dioxide and water it started with. But in doing this, the plant radiates heat, high entropy energy, dispersed, omnidirectional, useless for doing work. The total entropy of the plant plus its environment increases, always. Every living thing, every bit of order you see, is paid for by a larger increase in disorder somewhere else. You are an entropy increasing machine. You eat food, low entropy chemical energy, you metabolize it, break it down, use it to maintain your body's structure, to think, to move. And you radiate heat. You exhale carbon dioxide. You excrete waste. The entropy you produce is far greater than the entropy decrease represented by your organized body. You are a dissipative structure, a temporary eddy of order in a universe flowing toward disorder. Sean Carroll, a theoretical physicist at Caltech, put it this way. Every difference between past and future, he said, can be traced to the fact that entropy was lower in the past. Think about what that means. Every memory you have exists because recording information requires a low entropy state. Your brain is a recording device. For it to write memories, it needs structure, order, systems that are far from equilibrium. In a maximum entropy universe, memory would be impossible. There would be no difference between past and future because there would be no structure to record differences. The arrow of time isn't just thermodynamic, it's psychological. You remember the past because the past was lower entropy, and that allowed records to form. You don't remember the future because the future is higher entropy, and records can't form running in that direction. The arrow is built into your consciousness. You are made of dissipating order, and the fact that you can ask why is itself a product of that initial improbable state at the beginning of everything. And here's something even stranger. The thermodynamic arrow and the cosmological arrow align. The universe is expanding. Galaxies are moving apart. Space itself is stretching. And this expansion runs in the same direction as the entropy increase. Is that a coincidence? Maybe not. Some physicists think the two are connected. The expansion of the universe may be part of why entropy increases. As space expands, there's more room for particles to spread out, more room for disorder. The cosmic spring unwinds as the fabric of the universe itself stretches. But we still don't know why the spring was wound up in the first place. Why did the universe begin in a low entropy state? Cosmic inflation, the theory that the universe underwent exponential expansion in the first fraction of a second after the Big Bang, might explain it. Inflation could have diluted the entropy density, smoothed out the initial conditions, set the stage for everything that followed. But that just pushes the question back. Why did inflation happen? Why did the universe begin in the specific state that allowed inflation to occur? The answer, if there is one, lies beyond our current physics. The arrow of time comes from initial conditions, not from the laws themselves. And that's a profound distinction. It means the laws of physics tell us what can happen, but the initial conditions tell us what does happen. There's a subtlety here worth pausing on. You might have heard that the laws of physics aren't perfectly time-symmetric. There's a tiny asymmetry in the weak nuclear force. Certain particle decays happen slightly differently when you reverse time. This is called CP violation, or more precisely, CPT violation if you consider all symmetries together. Physicists discovered this in the 1960s, and at first people wondered if this was the source of the arrow of time. It's not. The asymmetry is far too small. It affects some rare particle interactions, but it can't explain why eggs scramble and cups shatter. The arrow of time is statistical, not fundamental. It emerges from probability and initial conditions, not from a bias in the laws. Think about that for a moment. The universe doesn't have an inherent preference for forward over backward. There's no clock in the fabric of space-time, no mechanism ticking in one direction. The arrow exists because of where we started, because the Big Bang was a low-entropy event of staggering improbability. Everything since then has been the inevitable, statistical slide toward more probable states, and yet that slide has been slow, incredibly slow. The universe is nearly 14 billion years old, and we're still nowhere near maximum entropy. The sun still shines, stars still form, life still metabolizes. The arrow still points, clear and undeniable. And it will keep pointing for trillions of years to come until the last stars burn out, the last black holes evaporate through Hawking radiation, and the universe reaches its final equilibrium. Heat death, the state where entropy is maximized and nothing can ever change again. But that's trillions upon trillions of years away. For now, the arrow points. And that pointing is what makes life possible. What makes memory possible? What makes causation itself possible? Cause precedes effect because the past is lower entropy than the future. You can scramble an egg because eggs are low entropy and scrambled eggs are high entropy. You can't unscramble an egg because that would require going from high entropy to low, and the universe doesn't do that on macroscopic scales. Not because it's forbidden, but because it's so unlikely that you'd wait longer than the age of the universe to see it happen once. And we are creatures of the arrow. We are patterns in the flow, temporary structures maintained by the constant influx of low entropy energy and the constant expulsion of high entropy waste. We exist because the universe is out of equilibrium. We persist because the spring hasn't finished unwinding. And we wonder about time, about why it flows in one direction, because we are conscious dissipative structures asking questions about the very conditions that make our existence possible. So can you imagine a universe without the arrow? You can't, not really, because in that universe there would be no you, no memory, no causation, no difference between past and future. Just timeless equilibrium, particles evenly distributed, temperature uniform everywhere, nothing happening, nothing to change, forever. That universe is where we're headed, ultimately, but we're not there yet. We're still in the brief, cosmically brief window where the arrow points, where entropy increases, where life can flourish and minds can wonder why. You drop a cup and it shatters. You can never unshatter it, not in any lifetime, not in any number of lifetimes. The pieces scatter into one of countless disordered states, and there they stay. Not because physics says they must, but because probability says they will. And that probability, that overwhelming statistical weight toward disorder, is the arrow. It's not built into the laws. It's built into where we started. The universe began improbably ordered, and it's been exploring the space of probable disorder ever since. We are part of that exploration. We are entropy machines. We are order temporarily sustained. We are the question the universe asks itself about why time flows. And the answer is this: time doesn't flow. There is no river. They are just states, macro states with high or low entropy, and we happen to be in a part of the universe's history where entropy is still increasing, where the arrow still points from low to high, from ordered beginning to disordered end. The arrow only points one way, and that's what makes every moment matter, every memory precious, every instant unrepeatable, because the spring is unwinding, and we are alive precisely because it hasn't finished yet.